This is the second lecture about communication for applied machine learning. And today we're going to talk about two things, probabilities and visualizations. And there was some watching posted that you could have done. Where are we? Oh my gosh. Here we go. There's some videos about visualizations that maybe some of you have watched, and if not, definitely recommend them for watching later on. So, oh, I thought I restarted. Okay. So announcements, homework 6 grades were posted yesterday, homework 7 grading is in progress, homework 8 deadline passed yesterday, and homework 9 was posted this morning. It's the last one where you write a blog post about what you did. So let us talk about confidence. And so the kind of machine learning angle here is that we've had predict, proba, and even for regression, well, we talked very little bit about prediction intervals. But basically, how confident are we supposed to be in our results when we build a pipeline and make a prediction? And this is an important question. And you know there's a lot of people making predictions out there, like election predictions and whatnot with probabilities. And so how do we think about all this? That's what we're going to talk about today. So let's think about this. Let's take it to be the case that Vancouver has the highest cost of living of all cities in Canada, which is probably true, unfortunately. And let's consider some different beliefs that we could have, or we could tell someone we have. So number one, you could say, Vancouver has the highest cost of living of all cities in Canada. I'm 95% sure of this. Or you could go up to someone and say, Vancouver has the highest cost of living. I'm 55% sure of this. And so the part in bold is called a credence. It's basically your level of confidence in something in the form of a probability, or how strongly you believe something. And which belief is better? Which of these you think would be more correct if you were going to go up to someone and say that? Someone said 2 in the chat. Depends on where you live. So this is what we need to talk about today. How do we evaluate the goodness of these type of statements? And likewise, what if it was actually Toronto that had the highest cost of living, and you went and made those same statements to a friend, which is better now? And where I'm going at with this is that if you're wrong, so if we're assuming the truth is that it's actually Toronto, and you go up to someone and you say something that's wrong and you're really, really confident, well, you kind of messed up because you said you were really sure, but actually you were wrong. And so in the second case, if it's actually Toronto, if that's the truth, this would be the better thing to go and say to someone, because if you say you're 50% sure, that means actually you're not too 55%. That means you're not too sure. You're only slightly away from 50-50. You're kind of saying to them, I don't really know, but if I had to choose, I guess I would choose Vancouver, which is kind of a less embarrassing mistake than saying something that was wrong and saying, but I'm really sure of this. And the kind of flip side of that, so actually the second one is maybe more intuitive and natural for us in our kind of human life. But the flip side of it is the first one. And if you're right, well, I would say then being more confident is better. I mean, if you go up to a friend and tell them something and you say you're pretty sure and they believe you and you were right, that's good. You kind of convince them of something that was true. Whereas if you tell them you're only 55% sure, you've maybe given them your perspective, but you haven't really told them that much, because you said, actually, I don't really know. I just think it might be this. But if you can be more confident when you're right and less confident when you're wrong, that would generally be a good thing. Any questions about that? People usually forget failures and remember your successes. Yeah. Okay. Always be confident. Well, no, that is not. When you do machine learning, don't always be confident. Make sure you're not overconfident. That's definitely part of the point here. Okay. So we want to be confident when we're right and hesitant when we're wrong. So what do these credences or beliefs actually mean? Well, like what percent should I say? So one possible definition is like I would accept a bet at these odds. So if you say you're 99% sure, that means you would bet $99 for a chance of winning $1 or something like that. And another possible definition of this is like correctness in the long term. So if you say you're 99% sure of something and you go around to 100 friends and to each one you say I'm 99% sure of something, then if you're making sense, you should be right 99 of those times and you should be wrong one of those times. And if that was the case, then it would make sense that you were saying 99% sure. So that kind of thing. So here's the thing. It's easy enough to evaluate how good we are at being right. So we've actually been doing that. Like when we take classification accuracy of a machine learning classifier, we can say, okay, you were right 80% of the time. But how do we evaluate how good we are at knowing how right we are? Meaning, how do we evaluate these credences? If you tell me a bunch of stuff, I can see how often you're right and wrong. But how do I evaluate whether the probabilities you're telling me, the credences you're telling me make sense? So that's kind of a very hard thing. And I would need to write down all the confidences, and I couldn't really assess it one time. But if I had a friend and I kind of watched them for 20 years and wrote down all their predictions, then maybe I could start to say, hey, this friend of mine is overconfident too often, or this friend of mine is underconfident too often, or something like that. And that's kind of an extra hard task that requires more information to assess, more data. That's right. So bringing this back to machine learning, well, it's kind of the predict versus predict proba. So if you predict that a credit card transaction is a fraud, well, the bank probably wants to know a probability. And so in real applications, you may be deploying predict proba very often because it's very useful to have that score rather than just a prediction. And so I've said this earlier in the course, but if your machine learning classifier outputs a 0.95 of predict proba, that doesn't mean you should go to someone and say, I'm 95% sure of this. Because, I mean, that 0.95 is very fragile. If you change the hyperparameters, you could get a totally different number. If you change what model you're using, you could get a totally different number. If you change what pre-processing you're doing or what imputation you're doing, you could get a totally different number. So the point of what I'm trying to say here is that when you go up to someone, like a client or a customer or your boss or a coworker, and you say, hey, I'm 75% sure of this, I want you to deeply engage with what it is that you're saying. And that's kind of the point of this lecture. And if your model says it's 95% sure, you might go up to them and say, well, the model says it's 95% sure, but I tried a bunch of different hyperparameter values and got ranges of things from 90 to 96, and I don't know, I'm 90% sure or something like that. And it could be true with regression as well. So in the homework 7, you did avocado prices, which is a regression problem. But you could say, for example, what's the probability the price will go up next week rather than down? And you could try to give a confidence there. Or what if you're predicting a house price to be 800,000 or an avocado price to be $1? then it's even harder because it's not really a true or false statement exactly. I mean, the house price is not going to be exactly this. And so we talked a little tiny bit about prediction intervals earlier in the course. And so you could try to use those quantile regression um, approaches we talked about to do like a 0.1 and a 0.9, and you could say I'm 80% sure it's in this range or something. But we mostly talked about it more for classification. Questions? Okay, so what I want to do is take you a little bit into the innards of logistic regression, because it's very related to this. Okay, there's a question in the chat. I was under the impression that quantile is for dealing with outliers. That is a complicated question. So quantile regression, such as 50% quantile regression, also known as median regression, is better for dealing with outliers, but that's not why I introduced it in the course. So there was the quantile transformer in the outlier lecture, and that was kind of a separate thing. But in the second regression lecture, I don't remember what it was, lecture 11 or something, I talked about prediction intervals where you wanted to say this, I predict this house price is between 750 and 800. And we used quantile regression for that as well. So we did like a 0.1 regression and a 0.9, a 10th percentile regression, 90th percentile regression, and looked at the predictions, and one said 750 and one said 800, and that's how we got our range. And that wasn't really about outliers. It was about getting a range in regression because you don't have a predict proba in regression, and the equivalent is kind of like a range or error bars on your prediction. Okay, so going back to logistic regression. So it turns out logistic regression actually has the same preferences as this Toronto, Vancouver thing we just talked about. Logistic regression would like to be correct and confident, or if not, it would rather be correct and hesitant. And if not that, it would rather be incorrect and hesitant. And the worst thing it can be is incorrect and confident, just like we talked about the Vancouver-Toronto thing. So I want to show you in scikit-learn, I can actually import the log loss, which is what is actually being optimized when you call fit on logistic regression. And it's not a score, it's an error. So lower values are better, kind of like mean squared error. And when you call fit, it tries to make this error as small as possible, which makes the score as high as possible. And I can just call this log loss function in scikit-learn. Okay, I haven't proven to you that logistic regression is actually using this under the hood, but you can take my word for it that it is. And I can just show you if I call this scikit-learn log loss function, and don't worry about the code. The code is a huge mess here. But what this is doing is it's saying, well, what is the loss or the negative score if you're correct and 95% confident? So it's saying the true thing is 0, and I'm 95% on 0, 5% on 1. That's what the code means. And it gives you some score. It's 0.05. We don't exactly know how to interpret that. But what I want to show you is if you change that to correct and 55% confident, meaning the true answer is 0 and you're 55% on class 0, then this number goes up. So it's saying this is significantly worse, because remember, this is an error. You want it to be lower as possible. So this is small. This got bigger. And now I can make it incorrect and 55% confident. So that I'm keeping the true answer at 0 all the time here. But now you're saying I'm 45% on 0, 55% on class 1. I should just clarify, these things over here are like the predict proba scores that you would give to the two classes for a particular training example. I should have said that earlier. So you have a single training example. The true class is class 0. Here your predict proba is 95.5. Here your predict proba is 55.45. Here your predict proba is 45.55. And the number's even higher, meaning that's even worse. And the worst possible thing is if you're saying 5% on the correct answer and 95% on the incorrect answer, and then you get this very big number. So it's like, I guess, what, almost 4 times unhappier, what in this case as this number in this case. But you could see between here and 0.6 and 0.8, it's not actually that much unhappier. And indeed, there's no discontinuity where logistic regression really cares if you're getting it right or wrong. If you're 49.999% or 50.001%, logistic regression actually doesn't really care about the difference between those. There's no sudden change in how happy it is when you start getting it wrong or right. It's only just looking at the probability. So 0.95, 0.55, 0.45, and 0.05. And if I plot this, and I can minimize the code here, this is actually what's happening with logistic regression. So there's some loss, which is like a negative score. The lower value is better. And 1 means you're 100% confidence in the right answer. That's like the best possible score of 0. And as you get less and less confident in the right answer, meaning more and more confident in the wrong answer, this number explodes. And so if you're at like 0.01, like if you're 1% confident in the right answer, meaning you're 99% confident in the wrong answer, it's really upset. It's giving you this massive error. And what it's actually doing is doing this for every training example and then averaging over all training examples. So if you have 1,000 houses in your housing data set, it's averaging over those 1,000 scores. And so what this is saying is it's going to be really, really upset if for a particular house, well, no, the house is not classification, sorry. For a particular transaction, bank transaction, if you're wrong and really, really confident, it's going to be very upset and try to avoid that. And so as you call fit, it's trying to do better on this for all training examples by trying to make it more confident in the correct answer for all training examples. And so, yeah, I wanted to just show you that to basically say under the hood, some of these classifiers are actually, they have this notion built into them that they're based on predict proba, not the predictions. And they're trying to make it as confident as possible in the correct answer. Questions? It's loss, so the original loss is even bigger. Could you elaborate? I'm not sure what you mean there. Oh, log. Oh, I see. Yeah. Yeah, I wouldn't really worry about the log aspect here. Yeah, I mean, sure. The actual number is something different, and this will be like some giant negative number. But we're just talking about the intuition here, anyways, not really the quantitative details, so it doesn't really matter. But yes. Okay. Yeah, and there's this fun link of how to assign partial credit on the exam of true-false questions, where there's, this is from Terry Tao's blog. He's a mathematician. He's saying, well, I can ask my students on a true-false exam to write down their confidence, and then basically grade them using this scheme that if they're really confident and wrong, then they're going to get a huge penalty on their exam. And it's just a kind of fun blog post. Okay. Yeah, so there's other examples you can look at where people are kind of making predictions and keeping track of how confident they were and whether they were right or wrong and stuff like that. So you can click on these links if you're interested. But what I'm really trying to get at here is when you call predict proba, there are actually quantitative ways of assessing how good that answer was. And this is one such way that logistic regression uses. And the theme is the more confident you are in the correct answer, the better. And that's kind of how it works. So I'm going to do an activity now in a Google Doc, again, like we did last time. And so here's how it's going to work. I have some claims below, and you're going to need to assign credences, like how much you believe something is. And so try to do it independently so you're not looking at each other's answers. So try to think about your answers and then put them all in the Google Doc. Oh, whoops, that's this. And try not to Google the answers. That kind of defeats the purpose. So I have 6 of these statements, and I'm going to give you the link in a second. But I am blank percent sure that the world's tallest building is between 200 and 800 meters tall. So you need to put in a number between 0 and 100%. And so if you're really confident that the world's tallest building is in that range, put a high number. If you're really confident that the world's tallest building is not in this range, put a very low number, close to 0. And if you have no clue, put a number close to 50%, because that 50% basically means I have no idea. 100 means I'm very confident this is true. 0 means I'm very confident this is false. And then, so for these 3, you have to put in percentages. And then for the last 3, I give you percentages, and you need to put in an actual number of meters. Do you mean how massive? 3 Mars. Yeah, weight. Yeah, right. Sure. Let's say weight. I have no clue. Okay. well, that might be more. Okay, let's say diameter. Sure. Okay, let's do that instead. All right, so I'm going to give you the link now. So here's the Google Doc. And this link is hopefully the right link. I just put it in the Zoom chat. I want to zoom in. And I'm going to move. Well, yeah, people are going to start answering, but don't look at my screen or the Google Doc while this is happening, because that's going to bias your answer. I'll give you around 5 minutes for this. I'm going to switch my screen over to the Google Doc, but I pasted all the questions in the chat. I just want to see how much we have. Oh, now I see why someone recommended a Google form. We could get nice statistics on this, like a histogram. Okay, I'll give you maybe a few more seconds, 10 seconds, 20 seconds. All right, time's up. So take a look at my screen on Zoom. I'm sharing the screen with the Google Doc. Okay, so here, let me see what we have here. So this 0%, I find maybe too extreme. If you put 0% sure that the world's tallest building is between 200 and 800 meters tall, that means you're 100% sure the world's tallest building is not between that, which means you're 100% sure it's either less than 200 or more than 800. And maybe you are 100% sure, but I just want to make sure that was the intention of the people who put 0, because I find the common misconception is that people put 0 when they're trying to say I have no clue. But if you have no clue, you should put 50. And think about predict proba. If predict proba has no clue which class it's classifying, it's going to do 0.5, 0.5. It's not going to do 0, 100, or 0, 1. And so likewise for the person who put 100, I guess that person's really, really sure. But I mean, now some of you in the class are putting 100 and some of you are putting 0. And so, I mean, one of you is infinitely wrong, because it can't be both. Someone put in the chat, 0% would be inverse confidence that you're, yeah, that's right. Okay, so let's see what else we have. Yes, we have all kinds of numbers. So yeah, I'm seeing a lot of zeros, and I just want to emphasize whether that if you put 0, that means you're sure this statement is false. So can someone look this up, by the way? What is the world's tallest building? Height? I'll just post it in the chat. 828. Okay. So I guess that's why the people put 0, maybe. But you know, I mean, how sure are you really? Like maybe in that case, you would put 0.000001, but or something. But is there a 1 in a billion chance that the building fell down in the last 5 minutes? Or maybe not. Is there 1 in a trillion chance that it's fake news? Yeah. So you know, you might still want to put 0.0000000001 because you never really know. And I guess that's kind of yeah, part of the fun of this exercise and part of the point, which is even if your tools, your machine learning, your Google, your whatever are telling you something, does that mean you as the human have that confidence? Well, you have to think about the entire world in a human sense to really answer this type of question. Awesome. Okay, let's move on to the next one. I am blank percent sure they're between 200 and 300 bones. So again, we have infinite disagreement, which is kind of fun. I'm seeing the numbers are pretty high here. So, oh, there's lots of zeros and lots of hundreds though. You folks are really at odds with each other. And some people are very overconfident. So I had to answer this specific question that we could. Okay, so some people are saying 208, 206. Okay, yeah, so maybe it's true, but again, I mean, okay, it's probably true, honestly, if that's what people are saying. But yeah, fine. Well, does anyone who put 0 here want to argue their case? You don't have to, but isn't it 402 for a child and then fuse into 206? Okay. Yeah, so I mean, this is all very interesting. Like maybe the question itself is ambiguous and there's like a 1% chance you misunderstood what I was asking or what your boss was asking or whatever. And maybe you want to take that uncertainty into account. Oh, it says adult. I see. Okay. So maybe some people missed that. But yeah, maybe there's even the own uncertainty that you misread the question that should be taken into account. Okay, next one. I'm blank percent sure the planet. I just love how every question has some zeros and some 100s. Personally, I wouldn't put 0 or 100 for pretty much anything for the reasons I described. I'm blank percent sure the planet Mars is more massive than the planet Mercury. I would guess that was true. So if it was me, I probably would have put, yeah, I don't know, 98 or something. Can someone post in the chat the diameters? Oh, and this had the old question. I didn't update it. Mars is 6,800 kilometers, someone posted, and Mercury's 4,800 kilometers. Someone's asking in the chat. Oh, sorry. Okay, yeah. So I changed the question in the Jupyter notebook from mass to diameter, but I forgot to change it here. So if you answered the old question, then that's my bad. Yeah, my bad. Okay. Could you please explain again why you would not put 0% or 100? Well, I mean, I just could have misremembered. Maybe I didn't have my coffee. It's just saying you're 100% confident is like a really intense statement. And as you could see in the logistic regression thing up here, if it's wrong and like it gets infinitely upset at you for being 100% confident and wrong. And so it would rather like be kind of wrong for every single training example in your whole data set than being like 100% confident and wrong for one training example, because that's just like the worst. I mean, I'm not saying you should live your life by the logistic regression loss function. That's just one way of quantifying this. But I guess I'm just trying to say saying you're 100% confident or 0% confident is a really strong statement. I did actually say that to my wife a couple months ago. I was like, I'm 100% sure of this, and I was wrong, and I was so embarrassed. So I learned my own lesson. Anyways, is there a real difference between being 99% and 98% in this situation? Great question. So here's the thing. If you put 98%, does that mean you are not as good as another student who put 99%? No, it doesn't mean that. I can't look at this and say this student is better than that student is better than that student. That's the wrong way of looking at this. What I should look at it is say, if this student, now I should follow that person around, look at all the things they say 99% about, and if they're right 99% of the time on those and wrong 1% of the time on those, that student did an amazing job. So in other words, this person who put 75%, there's nothing wrong with that if that person was actually 75% sure. If all the times that person says 75% sure, they're right around 3/4 of the time, then that person's doing an amazing job at specifying their confidence or their credence. And so, I mean, sure, this person maybe knows more about space than that person, but it doesn't mean they're better at specifying their credences. They might be worse. This person might be saying 99% all over the place and being wrong half the time, and they just happen to be right here. And this person might be super awesome at gauging their confidence. So in terms of, is there a difference between 99 and 98? Whatever you want to pick your percentages such that you're right kind of that often amount of the time, which is very hard to track in a human. But as I linked to, some people try, they make predictions and they put down their confidences and then they try to see if their correctness kind of matches their confidences. And again, to be perfect at this, it's not that you need to be right every time, it's that you need to be wrong as often as you say you're going to be wrong. Okay, looking through the chat. I mean, in exams, we have to be 100% sure in true, false, or multiple choice. Yeah, well, because you don't have the option to specify your confidence. I agree with this approach from the perspective of the analysis. However, when it comes to execution, it simplifies things to assume an absolute and then reevaluate when more data is available. Yeah, but I want you to think about these when you are applying machine learning and you try to communicate with other people about the work you did. That's the whole point of this. Okay, is that why brands like Lysol say it kills 99.9% of germs? I guess they measured it. I think in a sense using voting probability is better. It conveys more information. So let's go to the tree thing. I'm 99% sure the world's tallest tree is taller than blank meters. Yeah, so some people put 1 meter, and I would push back on that. And there was some discussion about that in the chat at the time. I would say if you put 1 meter, really? Like, so you're 1% sure the world's tallest tree is shorter than 1 meter? I mean, personally, I'm way confident the world's tallest tree is taller than 1 meter because I don't even need Google. I can look out my window. Oh, I see a tree taller than 1 meter. Okay, I'm very, very confident. So if I'm 99.99999% sure the world's tallest tree is greater than 1 meter, then I'm not 99% sure because I can't be two confidences at the same time. And so put another way, these 1 meter people are saying they're 1% sure all the trees in the world are shorter than 1 meter. Why are they 1% sure? That seems so high. Yeah, so some people put 100 meters, 200 meters. Yeah, 3 meters again seems pretty low to me. So if I had to answer this, I don't know what I would say, maybe 80 meters. I don't know. I'm pretty sure the world's tallest tree is taller than 80 meters, but is there a 1% chance I'm wrong? I guess. Or maybe I would say, I guess I'd say 50 meters. Can someone look it up? 115. Okay, awesome. Thank you. So for this one, I'm 90% sure. Your answer should be smaller than your answer to the, sorry, okay, so confused. Your answer should be taller than your answer to the previous question. So whatever you answered in this one, it would make sense for you to answer something taller in the next one. And if this first person 50 is the same as this person 60, then that's good. Yeah, so because the thing is, if you say a taller value, that's kind of a stronger claim. And so you should be less sure that's true. For example, to take to an extreme, if I think the world's tallest tree is taller than 1,000,000 meters, well, my confidence that that's true is very close to 0 because I'm sure there's no tree 1,000,000 meters. So as I take this number down closer to 0, my entry should go up and be larger. But it's pretty mind-bending. Okay, so people put, yeah, so this person put 1,000 meters. It's a little tall. Okay, yeah, seeing good looking answers here. So the 50% one is the one I want to draw your attention to. So for my 50% sure, I'm basically saying it could go either way. I equally likely believe the world's tallest tree is more than this value or less than this value. I'm 50% either way. And so answers that are close to the real answer, which is around 100 meters, are kind of, these people seem to know a lot about trees, or rather, know a lot about specifying their confidences. Yeah, that's right. So if someone put 100 meters here, yeah, know a lot about their knowledge about trees. Yeah, I think that is exactly what I was trying to say. Thank you. Right. Yeah, this now gets very confusing. But so for example, 1000 here or 500 is pretty tall. So they're 50% sure it's more than 500, 50% sure it's less than 500, but that's fine. So yeah, as you can see, this gets very confusing. You could kind of make a plot of the tree height and your probability, and you could kind of do that. But okay, what was the point of doing all this? Well, I thought it was fun. I don't know if you thought it was fun, but beyond that, I just want you to engage with this issue of talking about your confidence. Again, because your models are going to be outputting stuff like predict proba that will take the form of confidence scores or credences. And I want you to think about what that means. And I want you to think about it critically before you pass that on. Because again, why are we talking about communication at all in this course? Because you will probably not be working alone. And when you communicate to someone else, think about this type of stuff. Think about what you're really saying. If you're saying you're 100% sure or 90% sure or 10% sure, and it will make you more effective machine learning practitioner, I hope. At least that was the idea. Are there any questions before we take our break? Okay, so let's take a 5-minute break. I'll see you at 11:48. Okay, we're back. There were these videos from calling bullshit. I'm going to post my recording, so I don't exactly want to click on these links and get their videos inside of my videos. But what they talk about was how data visualization is becoming very popular in the news, and axes can be misleading. So they showed a plot where there's like two curves, but they were using different axes, and that was all confusing. Histograms can be extremely misleading because the things are binned, and if the bins are different sizes, then that can completely change what the histogram is saying. And the actual physical width of the histogram might not reflect the range of values in the histogram, which is very confusing. They talked about all kinds of visualizations being clever for no particular reason. These examples are really fun, so I definitely recommend you check these out. And it kind of goes to what we were talking about last class, don't make it about you. The people who made these visualizations were trying to show that they were clever, but they were not actually communicating clearly. And then there's this idea of the principle of proportional ink, which is super important for visualization. That's basically saying if a number is bigger, there should be more ink on the page if you're visualizing that number in some kind of bar graph. And then there's a couple of links here for those who are interested. I should add, by the way, I probably mentioned we're in the process of creating a minor in data science for undergrads. And then in terms of data visualization courses, so there is one in like the informatic sciences department or something. And then there's a new 4th year CPSC course in visualization. But what we're now creating that will be ready, I guess, maybe for next academic year, is a new data science visualization course, which would be more along the lines of what we're talking about here. I think it'll be DSCI something 320. Anyways, that hasn't all gotten approved yet or made yet, so it's not guaranteed it'll be launching next year, but I'm hoping it will, and it may be of interest if you find this interesting. So yeah, there'll be like the 4th year CPSC course that's like more technical computer science angle and visualization, and the 3rd year DSCI course that's more specific to data and data science visualizations. That's more similar to this. Okay, so here's what we're going to do for the rest of today. We're going to do an activity in the Google Doc again. And here's, wrong thing, sorry. We're going to load up the housing data again. And so for this, you're going to need to run some code. So When I'm done talking, you don't have to do it right now. You'll probably want to fire up the lecture notebook from the lecture repo. And so I just have this same thing that I'm shamefully copy and pasting over again, pre-processing the housing data. And then I'm going to say, well, let's compare scikit-learn's gradient boosting regressor to scikit-learn's random forest regressor for some different values of n estimators. N estimators, again, is a hyperparameter controlling the fundamental trade-off. Larger values means more complex models, more overfitting, better training scores. And both gradient boosting regressor and random forest regressor have the same hyperparameter, which is like the number of trees they're using. So I have some different values of n estimators, like 3, 10, 30, 100, 300. And I have some code here that loops through these different values of the hyperparameter. So it makes a random forest regressor with that number of estimators and fits it and records the train and test score in a list. And then it makes a gradient boosting regressor with that number of trees, estimators, and then fits it and puts the scores in the list. And I should have run it while I was talking, but I guess it doesn't take that long to run. And then what we're going to do is we're going to try to look at the plot. So we've taken the data set, we've fitted these two tree models on the same data set for different values of the hyperparameter. And we're going to try to conclude which one is better. Is random forest better, or is gradient boosting regressor better? And here's a plot to get you starting to think that I just made like a horrible plot. Okay, so here's my horrible plot. This plot is kind of really confusing because I'm not plotting random forest and gradient boosting on the same axes. So this plot is kind of useless for saying which one's better. I mean, I guess technically all the data exists somewhere in this plot, and I could painstakingly read the axes here and read the axes here and read the legend here and read the legend here and try to figure out which one's better, random forest or gradient boosting. But this is a really crappy plot. So your task for the next, say, 15 minutes is to do one or more if you have time, but to try to do one of the following three. So fire up the notebook, run the code so you'll have all the scores, and try to make a visualization that intentionally tries to look like random forest is better than gradient boosting in this situation. Or try to make a visualization that intentionally tries to make gradient boosting better than random forest, or try to make a visualization that makes them look equally good. And when you're done, screenshot or copy and paste your image and just paste it into the Google Doc, literally as an image. You can actually get Python to save the plot as a file and do it here, but honestly, it's probably easier to just screenshot it and then paste in the Google Doc. And then we're going to look at everyone's plot. So someone asked, like, only changing the limits of the y-axis. You can be as evil as you want. You can change the limits of the y-axis, the x-axis, and anything you can make a bar graph. Anything you feel like doing to mislead is totally fair game. And I did this same activity last term, and there was some really fun results. So yeah, you can get going, and I'll be monitoring the chat, and I'll also show you my own visualizations at the end. By the way, just in terms of getting the notebook up and running, I'm assuming many of you or most of you have been doing this, but in case you haven't, probably the easiest thing to do is go to the repo of the course and clone the repo, and then you can fire up the lecture 21 in Jupyter, which is right here. Recording is back on. So you've pasted your visualizations. The first section is people who decided to try to make random forests look better. I was puzzling over this first one. I mean, those don't look like the real score to me. So I'm wondering what the backstory is here. This actually looks like different data to me than this. Because for example, RF test was like around less than 0.9. So I'm not sure about this one. If it was you, feel free to elaborate. You can type anonymously into the document explaining. Let's take a look at the next one. Okay, this one's cool. This one's, yeah, I like this one. So this one's cutting off the x-axis up to 50, which is around like here on my plot, and then only looking at a train. And get out of this. Then it makes random forest look better. That's awesome. Nice work. This person kept them kind of separate, so it's kind of murky and hard to tell what's going on, but same kind of idea that the x-axes are only the kind of lower number of n estimators, and so it makes random forest look better. Cool. Same kind of thing over here, cutting off the x-axis. Oh, someone changed the scores. Okay, that wasn't the intention, but that's okay. Yeah, so here again, the x-axis being manipulated to just kind of a play. Oh, and see, this person was also using different axes on the left and right, which allows you to totally manipulate things. Although I don't really understand how the score is above 1 here on the right. So I wonder if that's a mistake, because the r² score wouldn't typically be above 1. I'm a little confused about that, where that's coming from. Someone just, I guess, picked a particular value of n estimators, and then the random forest was better there. So these people are trying to make gradient boosting look better. So here we have gradient boosting looking better. I think gradient boosting is better, so this is probably the easier one to make the case, but here we see the test score is higher. But what the people are doing here is they're cutting off the lower part of n estimators where the random forest is better, so that's cool. I like that. This one's nice. It's just like, oh, it's clearly better in every possible way. Okay, here's another one. Looks good. Yeah, looks good. Looks good. Create a visualization that makes them look equally good. Yeah, I like this. Just saturate the axes. So actually you can't see anything of what's going on. So we're just going to say they're equally good. I like that. Same kind of thing here. Score from 0 to 100. That's kind of nice. Because 100 is like a plausible range for a plot, but really it should be between 0 and 1, and then they just look kind of the same. Here they again, the scale is really zoomed out, and so they look kind of the same. Oh, this is cool. Okay, yeah, that's really interesting. Just cherry picking the few points where they're very similar and then really zooming out as well. Very nice. Some sort of meme, I guess. I'm totally clueless. Okay, awesome. Great job, everyone. I can show you my visualizations as well. I think they're pretty similar to what you did. So for random forest, better. I just chopped off n estimators to be only the small values, which is what many of you did. For gradient boosting, better. I just showed the whole thing, and I think it is actually better, so that one was fair. And then to make them equally good, I really messed with I put them on separate axes. Oh, I thought I calibrated them to be like right on top of each other. How did that happen? Well, that's kind of sad. Anyway, I had different axes on the left and right and kept tweaking it until they were right on top of each other. But now I'm wondering if maybe there's some randomness and I didn't fully set the random state, and so the scores were not the same every time or something. I tried to set the random state so that it would be exactly the same when I did it again. But anyways, you understand you could have different axes and that's super misleading. So recapping what we talked about today, we talked about confidences. That comes up especially much in predict proba for classification. You could extend that to multi-class classification where you have multiple probability scores adding up to 1. And kind of your own confidence and what are the factors and what does it mean to be 100% confident and 0% and all that stuff. And then we talked about visualizations. If you didn't get a chance to check out those videos, I definitely recommend it. Even after the course is done, they're really nicely done videos from the University of Washington. And the point is there's just so many ways you can manipulate the picture. You can change the axes, you can change the bins. There's all these kind of things you can do. And so this is important for you both as a consumer of plots and as a producer of plots. Be responsible and show and don't be misleading. And it'll make you a more effective machine learning practitioner. So that's it for today. We're out of time. I'll see you Thursday when we will talk about ethics.